So we are going to continue our discussion of time-dependent perturbation theory. So let us quickly recall where we are. So we are basically dealing with first-order time-dependent perturbation theory. And the essential aspect of time-dependent perturbation theory is that unlike time-independent perturbation theory, a time-dependent perturbation causes transition between stationary states. Okay, so to evaluate the transition amplitude, we set up the perturbation expansion and then directly calculated the coefficients d of t, and we found that the coefficients can be expressible as the matrix element of the perturbation h tilde of t prime between the final and initial states times an exponential factor e to the I omega fi, where omega fi is related to the energy difference between the final and the initial states. Okay, so this is in some sense a master formula that tells you how to calculate these amplitudes for such transitions. Okay, so this is a unique aspect of time-dependent perturbations, that they actually cause transition between stationary states of the unperturbed Hamiltonian. Okay, so then we generalized, we took a specific example of periodic perturbations, right? So we took h tilde of t to be some h tilde, which is this h tilde here on the right hand side is only dependent on space. Excuse me, and all the time dependence is in the periodic part e to the minus I omega t. And we simply plug this into the formula for df of t, and then we evaluated the probability of such transitions by calculating the absolute square of d. Okay, and then we asked ourselves the question, what happens if I wait for a long time? Right? So in other words, if you apply the external perturbation, wait for a long enough time, then something very interesting happens. This sine square over omega function that we found turns into a delta function. Okay, and then we derived a beautiful formula that tells us the rate of such transition. The rate is a very important quantity because these are all happening continuously in time, right? So as you supply the external electromagnetic field in a bunch of atoms, such transitions occur at a continuous rate, and it's usually convenient to express not in terms of probabilities, but in terms of rates, which is just probability per unit time for such transitions to occur, right? And then we derived a formula for the rate, and we discussed the physics of this by claiming that if this is the perturbation I start with, h tilde e to the minus I omega t, right? Then the kind of delta function that I get is basically delta EF minus EI minus h bar omega, which means that this delta function makes it clear that the final state energy is greater than the initial state energy. Okay, so basically what we are dealing with is called absorption. So what's happening is that the atom is absorbing radiation from the supplied external field and then getting excited to a higher energy state. Okay, if instead we have started with h tilde e to the plus I omega t, then we would have gotten what is called transition from a higher energy state to a lower energy state. Okay, so this is called stimulated emission. Okay, the first one is called stimulated absorption. The second is called stimulated emission. Okay, anyway, there is actually a third category that we will discuss later, which is called spontaneous emission, but this requires a little bit of technical aspects to be set up, which we will postpone for now. Okay, so we will continue at this stage, and let me remind you that if you have, for example, a cosine omega t or a sine omega t, which contains both e to the plus I omega t and e to the minus I omega t, then in general, both of these are possible. Emission and absorption are both possible. In other words, if you start with a perturbation h tilde of t, which is something like h1 e to the I omega t plus h2 e to the minus I omega t, then the rate is given by a sum of two quantities. The first quantity is obviously delta EF minus EI plus h bar omega. Okay, the second quantity is basically the matrix element of the second part between the final and the initial states, EF minus EI minus H bar. Okay. So if you want to discuss, for example, absorption, so you will deal with only this part. And if you want to deal with emission, you will only deal with this part. But in general, they are both present. Okay. So we will take up time-dependent perturbation theory from this point onwards. And then we are going to talk about what is called photoelectric effect. Okay. Photoelectric effect is simply, as you guys very well know, is basically knocking an electron out of an atom, okay, by an external photon. Okay. Now, I should be careful in the word photon here, because when I talk about photons, I'm necessarily talking about external radiation as being quantized. Okay. It turns out that I can very well explain photoelectric effect without having to quantize the external electromagnetic radiation. There are some problems for which I need to do this, but for this particular problem, I don't have to treat the external field as a quantized field. I can simply treat it as a classical field. In other words, the system that I'm trying to understand is an external classical electromagnetic field interacting with an atom, but the atom itself is a quantum mechanical object. Okay? So such treatments in physics are what are called semi-classical treatments. Semi-classical because you distinguish part of the system as being a classical object and the part of the system as being a quantum mechanical object. In this case, I will treat the atom as a quantum mechanical object and apply the usual rules of quantum mechanics. And I will treat the external field as a classical object. Okay. So in this module, we will basically set up the problem of photoelectric effect. And in the next module, we will continue this effect by trying to understand how exactly one calculates the probabilities in this case. Okay. So here I will talk about setting up the problem. So since I'm treating the external radiation as a classical EM field, of course, you guys should recall certain basic aspects of classical electromagnetic theory. First of all, the problem that we would be solving is considering a hydrogen atom in the ground state. Excuse me. Ground state. Okay, so this is our initial state. Just 1 minute. Okay, I'll back up. Yeah. So this is our initial state. What is the ground state of a hydrogen atom? Well, it is the state 1, 0, 0. Right? In other words, it is characterized by n equals the principal quantum number n equals 1, orbital quantum number L equal to 0, and n equal to 0. Okay. In the coordinate space wave function is basically the overlap of r theta phi 1, 0, 0, and this is psi of r theta phi. I'll put psi 0 because this is the ground state of the hydrogen atom. And this, as you very well know, is given by 2 pi h bar to the 3 half e to the minus r over 2a0, where a0 is of course my Bohr radius. Okay, so this is basically my initial state. So I have, and I don't need to talk anything more about this because this is part of the system that you understand very well because we discussed hydrogen atom at length in our quantum mechanics course. The other half of the system is a classical electromagnetic field, which again you well know from your classical E&M course, but I will simply recapitulate certain important properties. And I will also relegate certain aspects of this to the tutorial sessions, and I will also mention what we are going to do exactly in the tutorial session. Okay. So the basic ingredient of classical mechanics, that classical electromagnetism that we will be using is the fact that both the classical E&M Okay. The fact that we would be using is that both E and B, both electric and magnetic fields, are derivable from a set of potentials. Okay. The scalar potential phi and the vector potential A. Okay. So specifically, I know that I can express the magnetic field as the curl of the magnetic vector potential, and I can express the electric field as the gradient of the scalar potential. And if I'm not dealing with electrodynamics, if I'm dealing with electrostatics, this is all there is to it. E would be just minus del phi because E is an electrostatic field. But in the case of electrodynamics, I should also account for the fact that there is a magnetic vector potential. So the electric field is given by this particular quantity. Okay, so this is something that you probably recall very easily. The other thing that we would need is the issue of gauge invariance. Okay. Gauge invariance simply means that Maxwell equations are a set of 4 equations that tells you the dynamics of the electric and magnetic fields. And it turns out that by choosing different A's and phi's, Maxwell's equations remain the exact same things. Okay. Now, this is not a symmetry in the usual sense of, for example, a rotational symmetry where I'm actually rotating the coordinate system. This is gauge invariance is basically a redundancy in the description of the system. The redundancy in the definition of the variables used to describe the system. In other words, I can choose this phi and A and I will get the 4 Maxwell equations, or I can choose a different set of phi and A and I get the exact same Maxwell equations. So what are the different phi's and A's that we can choose? Well, it turns out that if you have any A, you can transform to a new A. Make sure my vector symbols are proper, which is given by the old A minus the gradient of some scalar function lambda. But not just this, I should also together transform my phi to a phi prime, which is equal to phi plus 1 over c d lambda dt, where lambda is the exact same scalar function. So this scalar function lambda, capital lambda that I've written here, is a function of both space and time. Okay. Of course, this is more neatly expressed in the relativistic notation. In terms of an A mu. Okay, an A mu is basically a 4 vector whose 0th component is phi over c, and the 3 vector A is the other 3 components, right? So in this relativistic notation, I simply mean A mu goes to A mu plus D mu lambda. Okay. Anyway, the point is we can use gauge invariance to actually make our life simpler. In other words, since there is a priori no preferred choice for A and phi, one can always use the notion of this gauge freedom to choose that A and phi, which will make our lives easy. In other words, what we can do is basically choose a gauge and work in this gauge. So specifically what we will do is choose what is called the Coulomb gauge. And in the Coulomb gauge, it is characterized by choosing an A which is divergenceless and phi is basically 0. Okay. Now this is not so unreasonable as you might think, because this phi equal to 0 simply means that I've chosen a scalar function lambda such that my phi prime is 0. Suppose if I start with a phi that is non-zero, then I can always transform to another phi prime such that my Maxwell equations are invariant. Now, if I want this phi prime to be equal to 0, then I better choose my lambda as some minus infinity to t phi of r d prime dt prime. Okay, if I choose it this particular way, then you can easily see that my phi prime will be equal to 0. Okay. So of course, I should also ensure that del dot A would be equal to 0, and we will explore this more carefully in a tutorial problem. We should choose a second gauge transformation such that del dot A is also equal to 0, but this second gauge transformation should not ruin phi equal to 0. And it is possible to do it this way. And this choice of gauge is called the Coulomb gauge, in which the divergence of the magnetic vector potential is 0 and the scalar potential phi is identically equal to 0. Okay, so then if I work in the Coulomb gauge, then my electric field is simply given by minus dA dt, because phi is 0, and my magnetic field is, of course, still del cross A. Okay, so choosing A now chooses E and B unambiguously. Okay, so basically we will work only with the magnetic vector potential A. Okay, so the problem of understanding what this external perturbation is in terms of electric and magnetic fields basically boils down to what is my magnetic vector potential. And in this case, I'm going to choose my magnetic vector potential to be a monochromatic plane wave. So I will choose A to be A0 some cosine k dot r minus omega t. Okay. So I remind you that k is the wave vector, which is inversely related to the wavelength of the wave, and omega is of course the angular frequency. Okay, and they are both connected via the relation omega is k times c. Okay, where c is the velocity of light. Okay, now one can understand what the constraints from the Coulomb gauge imply. Del dot A equal to 0. Now remember, the way you understand this equation, A is A0 cosine k dot r minus omega t. The A0 is a constant vector, right? So this doesn't have any spatial dependence. All the spatial and temporal dependence of this wave is contained in the cosine k dot r minus omega t. So the job of A0 is simply to tell you what is the direction of this vector. Suppose if A0 is along the z direction, then I will have A0 is to be z cap or something like that. So A0 tells us the direction of A. Okay. Now, what does del dot A equal to 0 mean for this wave? Del dot A for this guy is basically, now since A0 is a constant vector, the divergence, which is ddx and things like that, only acts on the cosine part, right? So it leaves A0 out. Dot del of cosine k dot r minus omega t. So this is minus sine k dot r minus omega t, right? Times the derivative of k dot r, which is basically k. Okay. In other words, I can write this guy as minus k dot A0 sine k dot r minus omega t. So the Coulomb gauge del dot A equal to 0 simply means, now del dot A equal to 0 implies that k dot A0 equal to 0. Okay. What does this mean? K is of course the direction of propagation of the wave. And what is the direction of A0 signify? Well, since E is minus dA dt, right? Since, okay, sorry, this is not showing. Just give me a second. Sorry about that. Sorry. So since E is minus dA dt, the direction of E is specified by the direction of A. And the direction of A is specified by the direction A0, right? So which means that k dot A0 equal to 0 simply means that the vector k and E vector are perpendicular. K is the direction of propagation of the wave, which means that the electric field is perpendicular to the direction of propagation of the wave. Okay. Similarly, B is perpendicular to A, right? Which means that both B and E lie in a plane that is perpendicular to K. Okay. So this is the statement that electromagnetic waves are transverse. E and waves are transverse. What does this statement mean? This statement means that the direction of E and B are in a plane perpendicular to the direction of propagation of the wave. Transverse is the transversality condition simply means that both E and B are perpendicular to K. Okay, so this is again something that you already. So this is a classical electromagnetic field that is interacting with the hydrogen atom. And the question is, how will I write down what this interaction is? In other words, what is this external perturbation? This external perturbation can be derived from the classical Hamiltonian, which is given by the interaction of a charged particle with an external magnetic vector potential. And this is given by P minus Q A over C quantity square divided by 2m plus E phi. Okay. And since in the Coulomb gauge phi is 0, this Hamiltonian simplifies. Now, why this curious quantity P minus QA over C? So recall from your electromagnetism course that in the case of a charged particle interacting with an electromagnetic field, you derive what is called a generalized momentum or a canonical momentum, which is related to the usual momentum m times v, as capital P equals P plus Q times A. Okay, so the Hamiltonian is basically a reflection of that particular fact. The derivation of this, again, we will postpone it to the tutorial. Okay, so in the upcoming tutorial, we will discuss two issues. The first issue is the choice of gauge that gives us, to demonstrate that the choice of gauge that we have chosen is actually a consistent choice. The second is how to write down this Hamiltonian that tells us the interaction between a charged particle and an external field A. Okay. So these are the two things that we will do in the tutorial. So now let us go ahead with the setting up of the problem of photoelectric effect. So using the Coulomb gauge, I can immediately set phi equal to 0. So this Hamiltonian H actually simplifies to 1 over 2m times P square minus QA over C whole square. So let me write down all the pieces separately. The first piece is P square. The second piece is Q square over C square times A square. Now remember that I'm going to treat the hydrogen atom as a quantum mechanical object, in which case this Hamiltonian is an operator that acts on the wave function. So I should be careful in writing down the Hamiltonian, right? So in classical mechanics, I can simply write this as 2 times A dot P. But in the case of quantum mechanics, I should be a little careful, because A is a function of coordinates and P is a momentum. And any function of coordinates and momentum do not in general commute. So I should write this as two different terms, minus Q over C A dot P minus Q over C P dot A. Okay. So remember that Coulomb gauge has two conditions. Phi is 0 and del dot A equal to 0. We have already used the fact that phi is 0 to simplify the Hamiltonian. So now we are again going to lead up to how to use the other condition of Coulomb gauge, which is del dot A equal to 0. Okay. Now, this is a perturbation. And in some sense, whatever is acting on the atom is actually a weak quantity. Now, the strength of the electric and magnetic fields, of course, are determined by the strength of A. Okay, the absolute amplitude of A, which is given by A squared. So I'm going to assume that this strength is actually quite small. In other words, any quantity that is quadratic in A can be neglected in comparison with any quantity that is linear in A. So if I look at this Hamiltonian, I have three pieces. Well, the first piece, P square, is a free Hamiltonian, so I'm not worried about that. But if I look at the A square piece and the A dot T piece and the P dot A piece, I can argue that since I'm dealing with an external perturbation that is rather small, and since E and B are determined by the A is basically the external perturbation, I can always neglect the A square piece compared to the A piece. So neglecting the A square piece, we have H equals, now this is simplifying even further, minus 1 over 2m q over c a dot p minus 1 over 2m q over c p dot a. Okay. So now we have to understand the action of a dot p and p dot a, and since this is an operator, I have to act it on some function and basically understand what these two operators are. Okay, and since I'm dealing with a hydrogen atom in the ground state, the charge is basically the charge of an electron. So in this case, q is basically minus e. Okay, so I can write my h further as p square over 2m plus e over 2mc times a dot p plus p dot a. Okay? So this is what I have. My Bluetooth is again misbehaving, so I have to reshare again. Sorry about that. Okay. All right. So now let me continue with this and understand what these two pieces are and what this operator really is. So let me look at the p dot a. And let me act on some function f. What is this operator? Well, in the coordinate representation, which is what I'm going to use, p is given by minus ih bar del. So this is minus ih bar del dot a f. Okay. Now, of course, we should not be hasty and claim that this is equal to 0 in the Coulomb gauge, because there is actually two different pieces hiding here. The del acts on both the a and the f, right? So I should write this guy as minus ih bar del dot af. Sorry, I should be careful. So this is del dot af, right? So this is basically f del dot a minus ih bar a dot del f. Okay. Now I can always throw away this part in the Coulomb gauge, because del dot a is identically equal to 0. This is a null operator. But of course, there is also one other piece here. So p dot a f is basically given by minus ih bar a dot del f. Okay. What is this equal to? This is basically minus ih. Sorry. This is basically a dot pf. Okay. So in the Coulomb gauge, p dot a acting on f is basically a dot p acting on f, because the other piece that comes from p dot a is del dot a, and del dot a is equal to 0 in the Coulomb gauge. So I can use this in the Hamiltonian, h, which is equal to p square over 2m plus e over 2mc times a dot p plus a dot p. Okay, so basically my h is now given by p square over 2m plus e over mc a dot p. Okay. The operator, the perturbation operator, is basically e over mc a dot p. So the h tilde or h tilde, whatever we have called it, is basically in our case e over mc a dot p. Now, what is this equal to? For the particular a that we are interested in, a for us is basically a0 cosine k dot r minus omega t. So my external perturbation for my problem is basically e over mc, right, times cosine k dot r minus omega t a0 dot p. Okay. I can further write this as e over 2mc. I can write cosine theta as e to the I theta plus e to the minus I theta over 2. So that's how this factor of 2 comes in. This is e to the I k dot r minus omega t plus e to the minus I K dot R minus omega T A0 dot P. Okay. So remember that the time dependence of the first piece is e to the minus I omega T, and the time dependence of the second piece is e to the I omega T. So remember from our discussion during the start of this module that if you have a general perturbation like this, then the e to the plus I omega T refers to the e to the minus I omega T refers to the absorption part, and e to the plus I omega T refers to the emission part, right? So this is where the final state is. The first piece is where the final state has a lower energy than the initial state for the e to the plus I omega T part. And for the e to the minus I omega T part, the final state has a greater energy than the initial state. So in our case, what is happening? In the case of photoelectric effect, you are basically knocking the electron out of the lowest energy, right? So basically, you are creating pushing the atom to a state that is higher in energy. So we have to deal with the fact that to describe photoelectric effect, we need to use that part of the perturbation which allows for the possibility for the final state to have a larger energy than the initial state. And this will only come from the e to the minus I omega T part. So for the photoelectric effect, the relevant part of this Hamiltonian is the e to the minus I omega T part. So I can now set up my perturbation theory using the Hamiltonian h tilde of t, which is equal to e to the 2mc. I will neglect the second piece because I'm not interested in the effects of e to the plus I omega t right now. So this is e to the I k dot r times a0 dot p e to the minus I omega t. Okay. So h tilde of t is basically h tilde of r e to the minus I omega t. Okay, this is exactly the same form as we used for the Fermi's golden rule derivation. In our case, the h tilde of r is of course given by e to the e over 2 mc e to the I k dot r a0 dot. Okay, so using this Hamiltonian, we will now understand the photoelectric effect by computing the rate of probability, or rather we'll first calculate d of t, which is the probability amplitude for the transition to happen. Okay, so we'll stop this module here and we'll continue this derivation by basically using this Hamiltonian and plugging it in the definition of d of t and evaluating d of t.